We were talking about generalized vector spaces, and what you're kind of generally asked to do is if someone gives you a set of something, they'll ask you, is that a vector space? And if it is, what's its dimension? And give me a basis for it. So those are usually the three things you have to do. Determine if it's a vector space, then find its dimension and basis. Something I didn't say, and it's pretty important in here, um, if if you're given a set that is a subset of a known vector space, you don't need to check all these axioms. You only need to check the two closure axioms. So that's much easier. Um, and if that little subset does obey the closure axioms, we call it a subspace. It is a vector space that is a subset of another vector space. Now that we've kind of gone through defining it, let's start going through how you would go about doing the three things I said you'll be asked to do. If the set is a subset of a known vector space, all you got to check is the two closure axioms. This is the checklist for is it a vector space? If it violates any of those 10 axioms, it's not a vector space. It's got to satisfy all 10. And if you're given a set that is, you don't know if it's a subset of a vector space or not, you've just got to check all 10 properties. When I taught this, and it was kind of quickly anyway, I never made my students do this third thing. So let's go about how you do some of these things. Remember when we did vector spaces for vectors, we had the ABC method and the 1-0 trick. We're going to use them again. Let's say our little set is 3x3 skew symmetric matrices. Skew symmetric means the transpose equals minus the original matrix. And they'll look something like this. They always have zeros on the main diagonal, and the upper and lower triangles are just mirror images, but negative. So that's certainly a subset of 3x3 matrices, right? So we only need to check the two closure axioms. So let's write a generic element using the ABC method. I can write a generic skew symmetric 3x3 matrix this way. A minus A, B minus B, C minus C, and zeros along the diagonal. How many letters did I use? A, B, C, 3. That's the dimension of this guy. If we find out it's a vector space, we know what its dimension is going to be. How many letters did I use? Now we'll use generic elements to test the two closure properties. Here's scalar multiplication. Multiply that generic element by a k. That means it goes into everything. And I can see that this result is still skew symmetric. I'm still in my set. Now I'll check addition. Here's a different generic element. I can't use the same letters on these two. I generate it the same way, but not with the same letters. Anyway, let's do that addition. I'll get this, and again, you see that this is in the same structure of, it's a skew symmetric matrix 3x3. So it obeys both the closure axioms. It is a vector space, and its dimension is 3. How do you do? Find a basis. You use the 1-0 trick. Here's that generic element. We're going to set A to 1, B and C to 0, and then in sequence. B to 1 and A and C to 0, and then finally C to 1 and A and B to 0. When you do that, these are the results. I could call each one of these, give it some notation, and then somebody says, hey, express this matrix, which is a skew symmetric matrix, using your basis. and I can do that. It's a linear combination of my bases. It's, in fact, this particular linear combination. Do a couple, I'll do two more examples. A set of all real valued functions, and we were told that's a vector space, but in which if the argument is 1, the function equals 0. Is that a subspace? Well, let's define a test function h to test the two closure actions. I'll say this h means I sum two functions that are of this subset. Give it the argument 1, that means I give each of these guys the argument 1. Because they're in that subspace, that just means 0 plus 0, I still get a 0. So it satisfies closure under addition. Okay, now I'll define my little test function as a scalar multiple of a member of that set. If I give it the argument 1, this f of 1 becomes 0 again, I get a 0. It also passes, it's closed under scalar multiplication. So this is a subspace, it's a vector space. It's a valid vector space. Let's try something that almost looks the same. Instead of this requirement, if the argument is 0, the answer is 1. Let's see if that works. Well, let's do addition. I'll define my test function as adding two generic functions of that set. Then I'll see what happens if I give it the argument of 0. Well, these guys are each 1, they equal 2 when you add them. That's not 1. So it fails the closure under addition. So right here, we know it's not a vector space, it's not a subspace. And just to complete it, we'll also test for scalar multiplication. Say our test function is k times some function of the set. And to make this turn out right, we can't just use k equals 1. It has to be generically. So if I plug in an argument of 0 here, the right side becomes k. And anytime k is not 1, I fail the test. The test has to hold for any and all. Anyway, even though these two guys look kind of similar, one's a vector space and one is nowhere near a vector space. That's it for chapter 3 of my little text. Next, chapter 4 is going to be determinants, but we're kind of done with systems of linear equations.